of minus omega tau. And you should know that tan of minus an angle, tan inverse of minus an angle, is minus tan of an angle comes from tan. So that's going to be equal minus tan inverse of omega. Oh, GC2. Oops, there's a 2 here missing. Please put the 2.
GD1.
No, GD1, sorry. Yeah. Put it on. Okay. So we found the GC1 part of magnitude and argument, and we know that I need to multiply the magnitude of GC2, and I need to add the argument to the argument of GC2. Okay? All right, let's move to GC2. GC2 of I omega is e to the minus I omega d. Do I need to do what I just did? Find the real part and the imaginary part, square root, the sum of real and imaginary. So Thomas says no.
One the real part, and then e to the.
Okay, Juan, if you got it, let me just go ahead and write what Juan is saying. I can rewrite this as 1 times e to the I times minus omega t. What form is that? Positive number e to the I something. It's a polar form, guys. It's already in polar form. Okay? Any complex number can be rewritten as magnitude e to the I argument.
What if you brought it down? I would have brought it down. Would it change? So it had like 1 divided by that. 1 divided by e to the I.
No, you don't divide. No, you don't want to divide.
I'm just rewriting it because it's a negative. Can you?
No, you don't want to do that.
Okay.
You absolutely don't want to do that. Because you have to form positive number e to the I something. That positive number is the magnitude. That whatever multiplies the I is the argument. So without any algebra, in this case it would have been silly to try to find the real part and the imaginary part. What's the real part? It's cosine of minus omega d. What's the imaginary part? Remember, e to the I theta is cosine theta plus I sine theta. Right? So you could go that path. You would get from minus square root of sine squared plus of cosine squared, which would give you the 1. But it's already in that form. Do you see it, guys?
Yeah.
Megan? Megan, okay? Make okay? So, from here directly follows that the magnitude of GC2 of I omega is 1, and the argument of GC2 of I omega is minus omega d. Okay? So, we are ready now to put together what is the magnitude of GC of I omega and what's the magnitude, or what's the argument of GC of I omega. So from star 1 follows that the magnitude of GC of I omega is of the magnitude of GZ1, which was absolute value of k over square root 1 plus omega squared tau squared times for 2, which is 1. So the magnitude, so the absolute value of k over square root 1 plus omega. And from the start 2 follows that the argument of GZ of 5 omega is equal to the sum of the argument of GZ1, which was minus tan inverse of omega tau, plus the argument of GZ2, which is minus omega. So we calculated what is the magnitude and what is the argument of GZ of 5. Clear, everyone? All right. So the body plot would have one plot is against log omega, the log of this, and the right-hand side plot would be against log omega, this. Let's look at what they would look like. Okay? William? Frequency can change from 0 to infinity. So log of frequency changes from minus infinity to plus infinity. Log of 0 is minus infinity, okay? Log of infinity is infinity. Let's look at what this is doing. We really have two asymptotes. How does this change as a function of omega? It's clearly a nonlinear function. But in the body plot, we have as x-axis log of omega. Okay? So what happens of log of this versus log of that? So log of the magnitude of GZ of I omega is going to be log of that ratio, which is log of the absolute value of k. Log of a ratio is the difference, right? Minus log of square root 1 plus omega squared. Clear, everyone? So what would happen as omega goes to 0?
Log of absolute value of k.
Yeah. As omega goes to 0, this becomes log of 1. Log of 1 is what?
0.
Any basis. Okay? So we get that log absolute the magnitude of GZ of I omega goes to log of the absolute value of k, which is a straight line of 0 slope. What happens as omega goes to infinity, very high frequencies? Well, obviously, this whole thing goes to minus infinity, right?
Yeah.
No question about it. It goes towards minus infinity. But we can give a little bit more information here. See how it goes to minus infinity. And one way I can rewrite this show you. No, I think you can see it. What happens as omega goes to infinity. Omega squared plus tau squared becomes so much bigger than 1 that 1 becomes totally negligible. So that becomes log of square root of omega squared tau squared. Both omega and tau are positive. So square root of omega squared tau squared becomes omega tau. I don't need to put an absolute. So we have here log goes to log absolute k minus log of square root omega squared tau squared, or log absolute k minus log of omega tau, or log of product is sum of logs. Okay? So I'm going to leave all those forms up here. What kind of an equation is that? That's an asymptote. What kind of equation is this asymptote? In a plot of log of magnitude versus log omega. Y-axis, log of the magnitude. X-axis, log omega. What kind of line is this? Straight line. And what's the slope of that line? -1. Exactly. So, I have more words, please. Everything okay as I erase? Everything's okay? Let's see. Darn it. No, I need this. I need that. But you have this. You have this again on this, so I'll erase this. So, what would that plot look like? It will have two asymptotes. It will have a low frequency asymptote, meaning as omega goes to 0, which will go to log absolute value of k. And it will have a high frequency asymptote, which will be a straight line with slope -1. With me? Where do the two asymptotes meet? So let me go back. I see some stairs, that means not everybody follows. As omega goes to 0, I'm going to the straight line log absolute value of k. This doesn't depend on omega. A constant is a straight line with 0 slope. So that's what I have as omega goes to 0, which means log omega goes towards -infinity. As log omega goes to +infinity, I'll have this equation. Yeah.
How do you get that equation if omega goes to infinity? Like how omega survives into the square root?
Well, because 1 plus omega squared tau squared as omega goes to infinity becomes omega squared tau squared.
Shouldn't it become just infinity? Shouldn't it-
Yes, it becomes infinity, but how it becomes infinity? It becomes infinity by becoming omega squared. Look, I have absolute value of k through 1 plus over square root of 1 plus omega squared tau squared. Divide by omega. If you divide by omega, becomes this, right? As omega goes to infinity, yes, the whole thing goes to 0, and the log goes to minus infinity. But as omega goes to infinity, what happens to this combination? 1 over omega squared plus tau squared becomes tau squared. So how does this go? K over omega over square root of 1 plus. This whole thing goes to, this disappears, so square root of tau squared, in other words, becomes absolute value of k over omega. Okay, so the log of this becomes log absolute value of k over tau minus log of omega. Okay, you can say that 1 plus omega squared tau squared behaves like omega squared tau squared as omega goes to infinity. That's all I'm saying.
Can you explain how that equation translates to that line on the graph? I'm not seeing that.
Yeah, so are you okay with this equation, right? Okay. So the variable here is what? K and tau are fixed, they're numbers. What's the thing that changes in the plot? Omega. Specifically, the x-axis is log omega. So what equation is that? Number minus x. Y equals number minus x. That's a straight line with slope minus 1. Okay? Okay? Proper champagne, okay? So, as omega goes to infinity, I'll have this straight line asymptote. Where do the asymptotes meet? They will meet when this equation, and let me take this form of that equation, becomes the same as this equation. At what omega this becomes the same value as this?
1 over tau. 1 over tau.
1 over tau. At omega equals 1 over tau, what happens to this expression?
Log 1.
This becomes log 1, becomes log absolute value of k, same as this. So this will intersect log absolute of k at the to intersect at omega equals 1 over tau, and this is called a corner frequency. You can say, well, because we have a corner. So the two asymptotes intersect there. Why are we using log omega in the body plots? Body plots exist from before computers. In the old days, you had to do everything manually. How would people draw the body plot? They would draw the asymptotes. What the real plot is going to be hugging the asymptote pretty close, far from the corner, pretty close, far from the corner, and it would be curving around the corner. So an approximate body plot is obtained by just drawing the asymptote. So you can see why you have log omega on the x-axis. That's the reason why body plots have log omega, although there's another reason I will talk about it. Clear, everyone? So that's the top plot of GZ1. Now, what is the body plot of GZ2? So that was, no, actually, okay, that's on GZ. Okay. But notice that, and I erased it, but. Let me finish doing that, and then I will come back. Okay. Everybody clear on this? So that's the log AR. How about